For the longest time, building really powerful AI has felt, well, a bit like magic, right? A bit of an art. But what if I told you that all that chaos is starting to end? That there's this one single elegant idea that's turning the art of AI into a predictable science. It's giving us, and this is no exaggeration, a periodic table for artificial intelligence. Let's dive in and see how this one idea is just completely changing the game.
So, is modern AI science, or is it really just alchemy? And that's a totally fair question to ask. I mean, we all know AI is ridiculously powerful, but for so long, building it has felt a lot more like alchemy than, say, chemistry. You mix a few ingredients, you try a few different incantations with your code, and sometimes something amazing happens. But the key thing is, you often don't really know why it worked. It's just a black box.
And this right here, this is the exact shift I'm talking about. We are literally moving away from that alchemy mindset of trial and error, just going on intuition, and we're moving into the chemistry of AI, an era where we can work from a set of actual fundamental principles. We can start to predict what's going to happen when we combine different elements because we're finally starting to understand the basic rules of the game.
All right, so here's the plan. First, we're going to look at AI's alchemy problem. Then we'll uncover the unifying principle that kind of solves it. We'll check out the actual table of algorithms this creates, and then talk about the control knob of AI. After that, we'll see how it can predict future algorithms, and finally, what this all means for the dawn of something called frugal AI.
Okay, let's kick things off with the problem itself, this whole alchemy thing. Why is a black box just not good enough? Look, I want you to imagine you're a builder. But instead of a nice, organized toolbox, you've got this massive, sprawling warehouse. And it's just filled with thousands of tools. None of them have labels. They're all kind of mysterious. That's what building AI has been like. How on earth do you find the perfect tool for the job when you're basically just guessing? And this image really shows you what that warehouse looks like. The AI landscape is this vast, complex ecosystem. It's a tangled mess of competing methods. And when you don't have a map, when there's no unified theory, trying to find your way through it is just so difficult. And it's not just inefficient, right? This actually slows down real innovation and wastes a staggering amount of computing power on ideas that just go nowhere. But what if? What if buried in all that complexity, there was one fundamental element, a kind of hydrogen of AI that's at the core of all these different methods? Well, that's exactly what researchers at Emory and MIT have found, a single breakthrough idea that connects almost all of today's most successful AI. Okay, so what is this magic ingredient? It's a mathematical principle called the information bottleneck. And the idea behind it is, honestly, it's deceptively simple. It turns out the smartest AIs aren't the ones that remember everything. No, they're the ones that are the best at forgetting. It's all about strategically throwing away the noise, compressing the data to keep only the stuff that's absolutely essential for making a prediction, and just tossing the rest. And don't just take my word for it. Listen to how Ilya Nimenman, one of the researchers at Emory, puts it. He says, and I'm quoting here, that many of today's most successful AI methods boil down to a single, simple idea. Compress multiple kinds of data just enough to keep the pieces that truly predict what you need. It's this beautiful, simple idea that's been hiding in plain sight this whole time. All right, so now let's see how this one single principle can actually bring order to all that chaos. This is the moment we go from an abstract concept to a real, practical tool, our periodic table. But before I show it to you, just take a second. What if there was a way to organize all of AI? Seriously, think about that. What would it mean if we could put every major algorithm onto a single, organized chart? What could we do with that kind of understanding? Well, here it is. This is the ICON framework, developed by researchers at MIT. And this is our periodic table of AI. Now, I know it might look a little complicated at first glance, but I promise you, the logic behind it is just so elegant. It takes dozens of famous, seemingly unrelated algorithms and organizes them all into one unified structure. Okay, so how does it work? The genius of this table is really in its simplicity. Just think of it like this. The rows. Those are the type of problem you're trying to solve. The columns, that's the shape of the solution you're looking for. And where a row and a column meet, boom, a specific well-known algorithm like CLIP or k-means just appears. They're not these random bespoke inventions. It turns out they're the natural logical result of combining a specific kind of problem with a specific kind of goal.
So if this is a periodic table, what's the atomic number? You know, the one thing that organizes everything? It's a mathematical idea called KL divergence. Now, don't worry about the fancy name. All it is, really, is a way to measure how surprised a model is by new data. And here's the kicker. Every single algorithm on this table, deep down, is doing the exact same thing. It's just trying to minimize its own surprise. It's trying to build a model of the world that's so good, that so perfectly matches reality, that it's never surprised by anything it sees.
Okay, so this table isn't just a cool theoretical idea. Let's talk about how it becomes a super powerful practical tool. One of the biggest hurdles in AI right now is dealing with different kinds of data at the same time. You know, multimodal data, like images and text together. Well, this framework has a really elegant way to handle that. The researchers who came up with this call it a control knob, and I love that analogy. Using that information bottleneck principle we talked about, you can basically dial in exactly what information you want the AI to pay attention to and what you want it to throw away. It gives you precise control, even when you're feeding it all these different streams of data. Let's make this super concrete with a simple example. How does an AI learn what a cat is? Well, it might get two different views. View number one is a picture of a cat, all that visual data. View number two is just the word C-A-T, so text data. That control knob, the information bottleneck, tunes the AI to fuse these two views together and only keep the shared essential catness. It learns to completely ignore the background color of the photo or the font style of the word. All that noise gets discarded, and it just compresses everything down to the pure core concept of cat.
Okay, this next part this is where it gets really mind-blowing for me. So, you remember when Mendeleev created the original periodic table of elements, right? He famously left these blank spots for elements that hadn't even been discovered yet, and he could actually predict their properties just based on the structure of the table. Well, this AI framework can do the exact same thing.
So think about it. If all these known famous algorithms are filling in the cells on this table, what about the empty ones? Are they just gaps? Mistakes? Or are they hinting at something more?
They are definitely something more. Those empty cells, they're not gaps, they are recipes. They are blueprints for creating totally new AI methods that don't even exist yet. A researcher can look at an empty spot on the table, see the exact combination of problem type and solution structure that it represents, and then go out and invent a new algorithm specifically for that purpose. We've gone from just discovering AI to actually designing it.
So, okay, a beautiful table, predictive power, but what does this all mean for the real world? Why should you care about this framework? Well, it's leading us to the dawn of something you could call frugal AI.
And here is your aha moment with hard numbers to back it up. In the MIT paper, the researchers used this framework to come up with a new little technique. On a standard pet dataset, the baseline model, SimCLR, got about 71.5% accuracy. Not bad, but with a small tweak that came directly from the Icon framework's logic, that accuracy shot up to over 84%. That is a huge jump, and it didn't come from throwing more data or more computers at the problem. It came from one small, elegant idea that the theory itself predicted.
And that right there is the real-world impact. Look, we always hear that AI needs these giant mountains of data and computers the size of a small country to run. This framework shows us there's another way. It lets us build more data-efficient models, which means they need less training data. They use less computational power, which makes AI cheaper to run and a whole lot greener. And maybe most importantly, this unlocks new avenues for research in areas where data is super rare, like for specific diseases or in certain fields of physics. We can finally start to design algorithms that just do more with less.
So really, it all comes back to this one powerful idea. As Ilya Nemenmin said, what this gives us is a kind of periodic table for AI. Every method has its own cell, and its position is determined by a very simple choice. What information does it keep, and what does it decide to throw away?
So this framework, it's not just a history book describing the AI we've already built. It's a map to the future. It finally, truly turns AI alchemy into chemistry, which leaves us with just one really exciting question. If this is the periodic table, what incredible new elements are we going to discover next?